At this time, I would like to welcome our science director, Dr. Jarrett Heiss, who will introduce our Nobel Day speaker. Jarrett?
Thanks, Connie. Let's set the stage for the transformational research and scientists we will learn about this evening. First, a compelling problem. Starting in the 1960s, Dr. Ray Davis studied our sun from almost a mile underground at the Homestake Gold Mine in Leeds, South Dakota, now Sanford Lab. By using 100,000 gallons of dry cleaning fluid, Davis detected roughly 1/3 of the expected number of tiny particles called neutrinos, establishing one of the most important questions of the time called the solar neutrino problem. As we will learn, an experiment called the Sudbury Neutrino Observatory, or SNO, was instrumental in answering that question. Second, transformational research requires an inspired leader to manage the many challenges of an audacious project and to wrangle a collaboration of scientific rock stars. I'm not sure what your wrangling experiences have been like, but that's no small feat. That leader is Dr. Art McDonald, co-recipient of the 2015 Nobel Prize in Physics. Art McDonald is a proud native of Sydney, Nova Scotia, in the far eastern part of Canada. He has degrees in physics from Dalhousie University and Caltech, and has held professorships at Princeton University as well as Queen's University, where he is now Professor Emeritus. Among other awards and recognition, McDonald is a companion of the Order of Canada, and with the SNO collaboration, he received the 2016 Breakthrough Prize in Fundamental Physics. Art McDonald's contributions to science have far-reaching implications in the field of particle physics. Through Art's leadership, the SNO experiment set an early benchmark for conducting the exquisitely careful science required for exploring nature's rarest processes. And in fact, this is another strong connection to the legacy of Ray Davis and theory collaborator John Bahcall, whose pioneering partnership was very much a testament to the careful science and perseverance needed. Dr. McDonald continues to be very active in basic research involving neutrinos and dark matter. Moreover, Dr. McDonald lends his name to the McDonald Institute, a Canadian hub for astroparticle physics research, uniting researchers, theorists, and technical experts within one organization. Art's contributions also extend beyond particle physics. An example for these pandemic times, Dr. McDonald worked with an international team of scientists on the design for a new ventilator for COVID-19 patients. SURF's first Nobel Day presentation was inspired by the 2015 Nobel Prize in Physics. So it is a great privilege and honor to announce this evening's Nobel Day keynote speaker and my former boss, Dr. Art McDonald.
Well, thank you, Jared. I'm about to try to share my screen, but I really want to first thank you for such a wonderful introduction. Jared was a graduate student on the Sudbury Neutrino Observatory project, and it's a tribute to the success of our project, not only in science, but also in education, that we now have one of our graduates as the science director at Sanford Lab. And congratulations on your own progress, Jared. I was asked to speak about the relationship between Ray Davis's work and the work that we did at the Sudbury Neutrino Observatory. Let me first ask Jared, is my screen projecting appropriately?
Looks good.
Okay, good. So The real question, particularly back in the 60s in the first place, is what powers the sun? What is it that produces this prodigious amount of energy in the sun? There were a lot of theories, of course, as to what was happening, and prominent among the theorists, and in the case of Willie Fowler on the right, the experimentalists who were studying the question of what are the nuclear reactions that power the sun, was the question of how you determine whether what is, in fact, the processes they had put forward, whether they are accurate. And they're complex processes. What I'm showing here is not something I expect you to understand in detail if this is a general audience I'm speaking to, but I would have you note that you start with 2 protons, the nucleus of a hydrogen atom, and through a series of reactions that occur because the sun has, by compressing the material contained within it to a very small central density and heat in the process, the energy there has been developed to the point where these 2 protons can fuse together, producing deuterium, which is in fact a hydrogen atom with an extra neutron, and eventually producing a pair of helium nuclei and atoms eventually in the central reaction set that occurs in the sun. The things that are outlined in red are neutrinos. As I would like to know actually the result of the previous poll on what this audience knows about neutrinos in the past. It would help me in terms of how I try to describe things as I go forward. But these neutrinos are, for those of you who said, what the heck is a neutrino anyway? I put up some facts here. Neutrinos are a basic building block of nature. Along with electrons and quarks, they are the basic particles that we don't know how to subdivide any further. And scientists always stop at that point. We say basic, but we're always willing to learn more if they are, in fact, able to be broken into smaller pieces, experiments to do that, we will certainly accept that. But as of today, they're the things that we know in terms of ordinary matter that make up us, make up the world around us. Quarks combine to produce neutrons and protons, which form in the nucleus of an atom. Electrons go around that nucleus and produce atoms. And neutrinos are produced when there are transitions that happen due to, for example, the very extensive reactions occurring in the sun and some radioactivity that occurs naturally on Earth. Neutrinos come in 3 types. The electron neutrino type is the type that's produced in the core of the sun. It's the only type for which there's enough energy to produce large numbers of them in the core. And in fact, they are produced in enormous quantities. These basic particles, neutrinos, electrons, and quarks, and the 3 types are the basis for what has come to be known as the standard model of elementary particles that has worked extremely well in terms of understanding our world on a very microscopic level. But neutrinos are unusual. They have no electric charge. They don't feel the strong interaction that quarks feel. And so they only stop if they hit the nucleus of an atom or an electron head on. And so they can pass through 1 billion kilometers of lead. That's the distance that light would travel in a year of lead and have only a 50% chance of stopping. So they pass very easily through the rock above our underground laboratories, but the cosmic rays that would otherwise make our detectors glow like the northern lights are in fact stopped by that rock. but the fact that they can pass through material without almost never interacting make them extremely difficult to detect. And so Ray Davis, in collecting 100,000 gallons of cleaning fluid, did that in order to increase the probability of detecting neutrinos. But even at that, he detected very few, in the a handful of neutrinos a month in his detector. And properties of neutrinos were not well known. It was known that you could study the sun using them, but exactly how many were produced in the sun was not known. And so that's what he set about to detect. Here's Ray and his friend and colleague, John Bahcall, the theorist, underground in the Homestake mine back in the 1960s. He started his development of his experiment in 1965 and had his first results in about 1969. These are real pioneers in the process of detecting solar neutrinos, and it is that pioneering effort that Ray was recognized for when he received the Nobel Prize. Here's the tank of cleaning fluid that they created, and he started detecting around 1968, and his process of detection was to use exquisitely low radioactivity or low interfering radioactivity detectors so that he could observe single atoms of radioactive argon produced when a neutrino, an electron neutrino specifically from the sun, came in and converted a chlorine nucleus into an argon nucleus. Those argon nuclei were swept out of this large tank with various gases that were circulated through it, and then put in these small detectors that he used to make his measurements. John Bahcall, on the other hand, was a pioneer in the development of detailed computer models for the sun and how many neutrinos would be produced in the nuclear reactions that power the sun, as well as the detection process that would be possible for neutrinos using chlorine in the way that Davis was doing it. And I actually knew both of them in my graduate days at Caltech between 1965 and 1969 in Willie Fowler's lab, actually, Kellogg Radiation Lab at Caltech. I met Ray Davis. He visited in the summer several times, and John Bahcall was a junior faculty member who I knew well and got to know even much better over the years. And it was a big topic, that is, this remarkable experiment that Davis was undertaking and the question of whether the nuclear physics was correct, both for how the sun was powered and how you might detect neutrinos with chlorine. And in fact, one of my fellow graduate students was studying the nuclear physics of chlorine in order to try to understand how Davis would be able to measure these neutrinos. Now, as Jarrett mentioned, Ray observed 3 times too few neutrinos compared to John Bahcall's calculations. But of course, he only measured one of the 3 types of neutrinos known to exist. And there was a theory that had been put forward, which would violate the standard model, but nevertheless could possibly be correct, saying that those electron neutrinos that Davis was looking for might actually have changed into one of the other 2 flavors before they reached the Earth or before they reached his experiment, and therefore they were not detected. And of course, there was also the possibility that either Davis or Bahcall, experimentally or theoretically, got it wrong. A big controversy over many years, referred to as the solar neutrino problem, as Jarrett mentioned. And in 1984, the Sudbury Neutrino Observatory collaboration was formed by George Ewan and Herb Chen. George from Queen's University. George actually passed away this week at about age 93. And he and Herb Chen, who actually passed away in 1987 at a young age, they put together the Sudbury Neutrino Observatory collaboration from working from an idea that Herb Chen had, that if you could get enough heavy water, which is instead of H2O, it's D2O, it's that deuterium again with the extra neutron in the hydrogen nucleus, then you could measure two things using that deuterium. First of all, you could redo Davis's measurement, potentially more accurately, and know the number of electron neutrinos that reached the Earth. But you could also measure all three types with no preference for any of the three, such that if in fact only 1/3 of the total were still electron neutrinos, you would confirm that Davis was correct, and in fact also that Bahcall was correct. And that's exactly what the Sudbury Neutrino Observatory observed in a pair of papers in 2001 and 2002. And our results showed that Davis and Bahcall were both absolutely correct, and the neutrinos were in fact changing their flavor. In 2002, the Nobel Committee awarded Ray Davis and Professor Koshiba from Japan a Nobel Prize in physics, noting them as being pioneers in the field of particle astrophysics, a large fraction of what the Sanford Lab's science objective is today. In 2015, they recognized the SNO project and the Super Kamiokande project and gave the Nobel Prize to myself and Takaaki Kajita as leaders of those projects for observing that in fact the neutrinos had changed their flavor. That observation is such that it requires that neutrinos have a mass which is finite, and that's different than had been predicted in the standard model and requires changes to it. So this was quite a radical result in 2002, and just to give you a feel for it and what it meant to John Bahcall and Ray Davis, let me play you a videotape of Bahcall's reaction in 2002 after the results came out from SNO.
I was called right after the announcement was made by someone from the New York Times and asked how I felt. And without thinking, I said, I feel like dancing. I'm so happy. And the one thing that my kids kept sending each other emails about all week was, did you see where it said in the New York Times that Dad felt like dancing? They kept making fun of me about that, but I was deliriously happy. It was, it was like for 3 decades, people had been pointing at this guy and saying, this is the guy that wrongly calculated the flux of neutrinos from the sun. And suddenly that wasn't so. And it was like a person who'd been sentenced for some heinous crime, and then a DNA test is made and it's found that he isn't guilty. And that's exactly the way I felt.
So John, in fact, was very pleased about this, and there are many people who would have expected John to also, along with Ray, receive the Nobel Prize at that time. There are actually restrictions on the number of people that can receive the Nobel Prize in any year. And in addition to Koshiba and Davis, there was an award made to a pioneer in the field of X-ray astronomy. So what is it that we did with the Sudbury Neutrino Observatory? We, starting with 16 people in 1984, we were able to build up a substantial collaboration and get funding in Canada, the US, and the UK predominantly for this experiment. As you well know, because of the experience there at the Sanford lab, these experiments underground are very massive and technically very complex. The heavy water that we used that was fundamental to what we were able to measure because of this deuterium content was worth $100 million. It's used in the Canadian-style nuclear reactor, the CANDU reactor, but there were reserves of it in Canada, and we were able to borrow $300 million worth for $1, which is pretty good leverage in any economic circumstance. We actually paid over $1 million in insurance for it. The idea was, in this case, instead of looking for the atoms produced as Davis did, we were looking for faint bursts of light produced in this heavy water in a transparent sphere and surrounding the outside and filling this cavern, which itself was about the size of a 10-story building, was ultra pure light water. We had to be very careful about the radioactivity and everything that we were doing, every part that we put in place. And what we had in addition was 9,500 light sensors that looked in at the central region here and were capable of observing very faint bursts of light. To give you the dimensions here, this is about 12 meters in diameter across the acrylic sphere here, or about 36 feet. The cavity was lined with material that made it waterproof and also suppressed the radon, the sort of thing that people worry about in their basements, was suppressed by the lining, which was one of the ways in which we were able to reduce the radioactivity content in the whole detector. Note that this heavy water is actually naturally occurring. 1 in 7,000 of the water molecules that you drink every day are actually heavy water. It's non-radioactive, but extracting it from ordinary water is quite expensive, as you can see from the price tag. So our laboratory, which has now been translated into SNO Lab, was originated by the creation of the SNO detector. Unlike Sanford lab, this mine in Sudbury is a very active nickel and copper mine, one of the most productive mines of the company that owns it, Vale. Thousands of tons of ore a day being taken out of the same shaft that we travel in as we are going to our work. It's about 6,800 feet, a little bit deeper than the Sanford laboratory. And so we had to build a new site, a new cavity, in order to then set up a detector that is going to see the following. This is basically what we're looking for. Nuclei fuse in the sun. They produce neutrinos. This one happens to be heading for Sudbury, going through the solar system, past the moon, and heading past the present surface building at the SNO Lab facility, and down to where our detector is, where it produces a faint burst of light. However, in order to get there, we had to go through a process somewhat similar to what's happening at Sanford as you prepare for the long baseline neutrino experiment. Excavation, here is the excavation of the 10-story cavity. This is looking down after the excavation has occurred and coating of the walls has been done with this waterproof material. It's during the construction of quite a remarkable device for holding the phototubes, which you see here as it was test assembled in California by a team led by Dr. Kevin Lesko, who I was pleased to see is actually one of the attendees in the audience this evening. Kevin not only played a major role in the SNO experiment, but also later played a leading role in the development of Sanford Lab, and he's now the spokesperson of the major dark matter experiment, LZ, that's in operation there. After having completed the top half of that support structure for the phototubes, which you can see here, supporting phototubes looking inward at the vessel, we had to put together the vessel itself, which involved very careful gluing of 120 panels, and eventually were able to complete that. And you can see some pictures here showing the light sensors, the detector as it was almost complete, and the full detector with ready for cables to be, well, I guess there are cables on it as it's ready to go. Everyone coming in for the construction took a shower and changed into clean clothing in order to maintain the ultra clean conditions that we had in the whole cavity and in the whole laboratory, in fact, that's mimicked now in the SNO Lab facility. The water, both the heavy water and the light water outside it, had to be purified extremely well, to the point where it's about 1 billion times cleaner than tap water. The radioactivity in all the materials were very carefully measured. And I really want to note that Bruce Cleveland, who was a very close colleague of Ray Davis, and in fact, a number of the definitive papers from their collaboration have Bruce as the first author, is still active in his work at SNO Lab. He's focused on very accurate measurements of the radioactivity in materials for experiments there. We had a special visitor in 1998, again in 2012, and the mining company, which was very pleased to have such a visitor, designed a special rail car so that he was vacuumed off before he went underground and didn't have to go through the shower process once he got there. Stephen Hawking, of course. Now, the final phase of the project was quite remarkable in the sense that we wanted to put and install in the middle of this $300 million worth of heavy water, about 400 meters in total, almost a half a kilometer of neutron counters that were themselves very low in radioactivity. They were flown into place, as it was put, by a small submarine. And anybody over the age of 23 and outside the video game generation was not very good at that. But fortunately, we had lots of young people, in fact, I think including Jared, if I remember correctly, who were expert at it. You may notice, here's the original submarine. You may notice a slight difference in color. And the reason is that we had a choice of colors, and if you have a choice of picking your right color for your submarine, particularly if you're a Beatles fan, a yellow was the obvious choice. However, that maybe wasn't the best choice because it turned out the yellow paint was much too radioactive and we had to remove it. Now, a number of the SNO collaborators who were involved in the development of these neutron detectors went on to play substantial roles at Sanford Lab. Of course, there's Jarrett, the person who introduced me, who's a scientific director now, but John Wilkerson, Steve Elliott, Hamish Robertson, who is also on the call, I believe, this evening in the audience, John Orell and a number of others from SNO were very instrumental in the Majorana demonstrator experiment that has been very successful here at Sanford Lab. So there's been a strong overlap between SNO and SNO Lab and the Sanford laboratory going forward. And it's really a pleasure for us at SNO Lab to see this very successful additional laboratory here in North America for cutting edge experiments. And certainly there is so much interest in the field that having several laboratories capable of providing these low radioactivity locations has been a worthwhile thing. This is SNO Lab as it stands now. This area on the left is where the original snow cavern was. There was a new area excavated at the same level, 2 kilometers down. There are experiments in all of these areas now, and here's a list of them. Many dark matter experiments you can see, an experiment for supernova. SNO has been repurposed for measurements of double beta decay and other solar and geoneutrinos by replacing the heavy water with a liquid scintillator. The low background facility where Bruce Cleveland does a lot of work is here as well. And there's room for a new large-scale project, Super CDMS. We're expecting to start installation within the year. It says at the bottom here that all of the lab air is class 2000, in other words, ultra filtered. This just gives you a scale of this large area called the Cube Hall. Shortly after it was excavated and the walls coated, this is what it looks like from ground level right now. This is the Deep 3600 dark matter experiment and the mini clean experiment beside it. If you look down from the top, you'll see there's a lot of instrumentation associated with it, and the other view that you got from the bottom is mainly the radioactive shielding on it. This is an example of another experiment in the facility where cleanliness is maintained throughout. So let me finish by saying that the fields of neutrino physics and particle astrophysics in North America, which, as you know from what you're observing at Sanford, are really rapidly growing fields of study in physics and right at the cutting edge of a number of questions of a fundamental nature. Everyone in the field owes a lot to pioneering scientists like Ray Davis and John Bahcall at Homestake, and George Ewan and Herb Chen for the initial developments in Sudbury. And of course, there are many others who developed these long-term laboratories, including Kevin Lesko that I mentioned before, and David Sinclair, who was the founding director and construction boss of SNO Lab when it was being developed. So it really is fun to see the way in which these fields have developed, and these low radioactivity environments are providing opportunities for very fundamental measurements, and it's a real pleasure to me to see how this has developed over many years. So thank you very much. So, Jared or others, I think you were planning on a Q&A at this point.
Correct. Well, thank you, Art. That was a nice trip down memory lane. Lots of fun times there for me, and I'm sure for others as you called them out in the audience. We are gathering some questions in the Q&A, so let's dive in. And if they start coming too fast and furious, I'll apologize up front if we don't get to your particular question. But with that, let's dive in. We got a few minutes here. Let's tackle the one here from the top that is asking about neutrinos produced in the sun. So the electron neutrino is produced in the sun. Are there other types, the muon or tau neutrino, and or their corresponding antiparticles? Are they produced in the sun or not?
No, it appears as though only the electron neutrinos are produced in the sun. In the case of the muon and tau neutrinos, there simply isn't enough energy in the nuclear reactions for the reactions that produce them involving mu and tau particles, as opposed to neutrinos, to be produced in the sun. And therefore, it's explicitly electron neutrinos. The question of whether there are anti-neutrinos, electron anti-neutrinos produced in the sun is a question that's been a subject of study. There are physics questions to be answered by studying them, but so far it appears as though the flux is far smaller. The limits that have been set are far smaller than the observable fluxes, which themselves are not very substantial. I think we observed roughly 1 neutrino an hour in each of the 2 reactions that we were studying in this 1,000 tons of heavy water.
Very good. All right, let's queue up the next question here. This one's about the NCDs, or the SNO neutron counters, those almost half a kilometer of neutron counters. The question here is, what were they made of to ensure that they had low radioactivity?
Well, ironically, given the mine, they were made of nickel. And Hamish Robertson and his team determined that if you produce the tubes that form the body of the detectors, there's helium-3 inside them, which is a very good way of looking at a nuclear reaction where the neutron has a very high probability of interacting with the helium-3 nuclei. That's a different isotope of helium, different from the normal helium-4. Those tubes were produced by having an organic vapor of nickel, let's say a vapor of an organic material containing nickel. And it was, they call it cracking. It was cracked onto other tubes by having it basically broken apart by heat, such that you ended up with a coating of the tubes. And so these tubes were formed by this process, which eventually deposited many thousandths of an inch of material, and then they were removed from the underlying tube and handled very carefully to keep them radioactive free before they were installed in the detector in Sudbury. And they basically didn't add anything to the local radioactivity, even in comparison to that ultra pure heavy water that was in the central region. And I mentioned how pure it was previously.
Very good. Actually, I want to loop back to one of the first questions, actually the first question, follow-up question on mu and tau neutrinos. So if they're not produced in the sun, how and or where are they produced?
Well, they're certainly produced. I'm sorry, would you say that again?
I'm sorry, say that again. Question is, so we talked through the types of neutrinos produced in the sun, and we ruled out the muon and tau neutrinos being produced in that location. This question is, where are they produced if they're not produced in the sun?
Okay, so they were produced. Oh, I'm getting some feedback, Jared. Anything I can do about that?
You're cutting out a little bit.
Okay, I'll try it again. I'll get a little closer to the microphone. Sounds as though someone else has a. Maybe if all of the panelists would make sure their microphone is off, it might work. So they were produced originally at accelerators, and in fact, a Nobel Prize was awarded for the discovery of other neutrino types. But they are produced in the atmosphere by cosmic rays. And in fact, the other half of the Nobel Prize that was awarded in 2015 was awarded to the Super Kamiokande experiment in Japan, where they observed that the muon neutrinos produced in the atmosphere changed into other types, predominantly tau neutrinos is thought, as they traversed the Earth. And so there are substantial numbers of, well, in their energy range, there are many fewer than the solar neutrinos, in fact, but there's enough that they are able to be detected in very large, in this case, pure water, ordinary water detectors, about, I think, 7 times larger than the SNO detector. And a very clear signal was obtained that the muon neutrinos traversing the Earth changed their flavor as well, which is what led to the Super Kamiokande experiment and Takaaki Kajita also being awarded the Nobel Prize.
Unmute. Very good. Thanks, Art. Let's see, next question here. Let's move on to the water purification system. How is that done? Is it done in situ, or is it transported from another facility where the purification is done?
So it was done in situ. I don't know if you noticed the large amount of piping that was in one of my slides, just above the picture of Stephen Hawking. Actually, he's right beside it as well. There were a number of sophisticated processes used for the purification, principally ion exchange media that were in an area underground that was a very significant amount of piping, and in addition there was a process where we would degas the water in order to remove both oxygen and radon. Oxygen to avoid biological fouling of the experiment, but radon in order to reduce the amount of naturally occurring radon that you find in water. And so all of that equipment was underground, very near our detector.
We were fighting mutes here. All right, next question. How long does it take for a neutrino to change type or flavor?
How long does it take? Well, it's more a question of how far it travels, and the parameters that come into it are the distance over which it has traveled divided by its energy, L over E, as we say in our equations. It turns out actually that we think that the dominant process was a change in neutrino type in the sun itself, such that by the time they emerged from the sun, and there was a certain amount of enhancement of the process through the interaction with the very dense electrons that you find in the core of the sun. But by the time they leave the sun, the mechanism is such that there's very little change before they reach the detector on Earth. And so timing it is well, you can figure out roughly what the time is if you say that they were traveling at roughly the speed of light, and you're dealing with roughly the radius of the sun as they go through it to get out. And so that's the time over which they would have done the changing.
All right, good, thanks. Here's a question from Hamish. Should there be another solar neutrino experiment to measure PP neutrinos? And he also adds in parentheses, Peggy says hi too.
And I would note that this day 5 years ago, Hamish and Peggy, who was actually a graduate student with me in the same laboratory at Willie Fowler's at Caltech back in the 60s, and Kevin Lesko and his wife we were all together in Stockholm on December the 10th, 2015. And we had a wonderful time at that point. Yeah, there's been quite a remarkable experiment at the Gran Sasso laboratory in Italy called Borxino, which has made measurements of much lower energy neutrinos than the ones that were observed by Ray Davis in the SNO experiment. And in particular, that first reaction, the PP neutrinos, that reaction is producing very low energy neutrinos, and it's very difficult to measure it. They have reported a measurement of those PP neutrinos, and I think certainly there are others that would attempt to do so, but it's a very difficult experiment. The SNO detector is now being converted by putting liquid scintillator in it, which means that it ends up with a very similar configuration to what the Borxino experiment had, which also has liquid scintillator. But whether or not we're able to control the radioactive background in as exquisite a way as the Borxino experiment did remains to be seen. And certainly the Camland experiment, which is a conversion of Kashiba's original water detector, for which he received the Nobel Prize from detecting a supernova, It's also been converted to liquid scintillator, but they've also found it very difficult to try to get low enough energies to observe those PP neutrinos. They're very important, however, to try to understand fundamentally how the sun burns.
Very good. Actually, we're getting quite a few questions. We'll try to knock some of them out here. Which one to go with? One here from Facebook. Have you discovered any clues about dark matter at SNO Lab? There's a few on dark matter as well. We'll cut over to that for this one here.
Well, not at SNO, but as I mentioned, a number of the experiments that are ongoing at SNO and ones planned for the future are aiming to attempt to observe dark matter. In fact, one of the two leading experiments in the world in terms of sensitivity for dark matter detection is in fact the LZ experiment here at Sanford lab, for which Kevin is the spokesperson. We have been at SNO Lab, we've taken a somewhat similar approach to what's being taken in LZ, but using liquid argon rather than liquid xenon, which gives you a slightly different sensitivity, and so we don't have a sensitive limits as they have been able to obtain in lux. But of course, if either of the experiments were to observe something, it would be valuable to have a different technique, but with similar sensitivity. We think with our future experiments at Gran Sasso and ultimately SNO Lab that we will be able to get into the same sort of sensitivity as future experiments using xenon. The PICO experiment at SNO Lab, which looks for bubbles formed by dark matter particles, actually has the most sensitive limit right now for dark matter that interacts via a spin-dependent interaction. The problem, of course, with dark matter is we have no idea what it is. There are lots of models as to what it could be, but what you really need is to try to go at it in a variety of different ways to see if different materials that it's colliding with or other techniques where you look for different properties might make a difference in terms of your sensitivity, but no one has seen anything yet.
All right, very good. There's a question here about why heavy water was chosen for SNO.
Well, that was well, it had been known for some time that deuterium had unique properties with respect to the detection of neutrinos, but it took one of our founders, Herb Chen, to have the audacity to ask if there was any possibility of borrowing. At the time he first put the question, it was, I think, $1.2 billion worth of heavy water for such an experiment. We subsequently were able to get that down, design the experiment in such a way that what we could get on loan, which was $300 million worth, was enabled us to do the experiment. But what his insight was is that if in fact you use deuterium, you can study two nuclear reactions induced by neutrinos. The first one, in which an electron neutrino strikes the neutron in the deuterium nucleus, it's a proton and a neutron in the deuterium nucleus, strikes that neutron and produces a fast-moving electron that we can observe as a burst of light in our detector. And the second reaction, which is sensitive to all neutrino types rather than specifically electron neutrinos, is one where the deuterium is simply broken apart. Proton and the neutron are broken apart, leaving a free neutron in the deuterium or in the heavy water. And that then produces a different burst of light. And in particular, with those wonderful neutron detectors that Hamish and his team put in place, we were able to observe those neutrons directly. Jarrett, did you ever get to fly that submarine?
Yes, yeah, I did actually. I spent quite a bit of quality time with that.
I think you did, in my memory, and I certainly remember the frustration of some of the older members at not being able to do it the way you young guys could. I think Davis was one example.
Yeah, we had to ban Davis.
There was a level 2 ski instructor at the same time and couldn't figure out why he couldn't keep up with you.
Quick comment here from Kevin, basically saying, thanking you for the kind words and for guiding SNO to success. But I do want to try to get, we're on our last few questions here. Maybe a quick one.
Thank you very much.
Have you ever been to Sanford Lab?
Yes, just once, and many years ago. I think it was at a point where it was still in the early stages of development. I did get to see, it was before the Davis experiment had been removed and replaced, I think, by Lux. But I was able to see these beautiful radiation detectors that Ray had developed, and how he was using them in his underground location. And so certainly it would be nice to visit at some point after we get this COVID crisis sorted out at some point in the future. I'm very impressed with what has been done in terms of the experiment so far, and also the experiments to come.
I know that you would be, there's a welcome mat out for you anytime that you're able to visit us. We'd love to host you.
Thank you.
I think we're going to maybe one quick, there's a couple questions here on sterile neutrinos, and then I think we'll turn it back over to Connie. So maybe just say a little bit about sterile neutrinos. Are they a dark matter candidate? Is the flavor of some of the questions.
In some theories, it is possible to solve to match the gravitational data that's obtained astronomically by the use of sterile neutrinos, and therefore it's a topic of significant interest. There are particularly experiments at Fermilab that are looking for sterile neutrinos, because they have there have been some hints that such neutrinos may exist. These are neutrinos that don't interact in the same way that the three active types, electron, muon, and tau neutrinos, do with matter, and therefore have to be observed in very different ways. So I think the next generation of experiments that are being created at Fermilab have the opportunity, I believe, particularly having a near detector of high quality that will determine what the properties of the neutrinos are as they leave the accelerator, as well as a very large detector, which is also liquid argon, as will be the big dune detectors eventually for the long baseline. Or that combination of detectors should be quite definitive about the particular region where sterile neutrino evidence has been reported before.
Very good. Very good. Thank you. Well, if we didn't get to your question, for those, and we didn't get to them all, we can follow up later and try to provide you an answer. So thanks for all the interest from our audience. Thanks, Art, for the wonderful talk. It was great to see you again. Great to visit again about SNO. I'm going to turn it back over to Connie to wrap things up.
Well, thank you, Jarrett. Oh, Dr. McDonald, thank you so much. What a terrific presentation. And just let me join Jarrett, and I know Mike Headley, in saying you are welcome here anytime. We would love to have you and have you here and show you all of the new things that have happened at SURF. In fact, in 2016, which was just less than a year after you'd been awarded the Nobel Prize, we tried to get you here as a speaker, and they said your schedule was pretty full. I wasn't sure why that was, but we're so happy we were able to get you here this year.
Well,
Thank you.
it's crazy. I was traveling almost 50% of the time for quite a few years. And it just didn't work that time. It would have been.
We are so honored to have you here tonight. Thank you so very much. And I also want to thank one more time our wonderful sponsors whose generosity helps SURF's team offer fantastic K-12 programming and wonderful community programming. We simply could not do this without the help of our fantastic sponsors. Finally, I want to thank our terrific SURF team. From Mike Headley to Stacy to my communications team, Matt and Aaron and Nick. You just make all of this possible. And I also want to thank Jarrett and our fantastic viewers who are with us all the time. And we so appreciate you sticking with us through this difficult time. Thank you and have a great night, all of you. Good night.
Good night. Thank you.
Thank you.